nanohub.org.
Online simulation and more for nanotechnology.
All right, guys, let's get started. Today's lecture is going to be a new topic. It's the first real uncertainty quantification method that we're gonna look at. I mean, Monte Carlo is considered, I don't know, an uncertainty propagation method, but it's a rather trivial uncertainty propagation method. Straightforward, you just sample the hell out of what you have. It always works, but you may not be able to sample a lot. But anyway, today's the first time we will start introducing things that are a little bit more complicated and they have a little bit more math. Even though this particular topic, perturbative methods, is the most easy. It's the easiest. Okay, you'll see next time it will become more and more challenging, but it will give you more powerful ways to propagate uncertainties. So, unfortunately, I didn't find a book that discusses this to the level that I want. So the only reference that you're gonna have is going to be the handout that I'm not actually handing out, but it's on the GitHub repository. So whatever I have written there is what you should refer to, and this holds for pretty much most of the lectures from this point on. So perturbative methods for propagating uncertainties are quite simple. You take whatever you want to propagate uncertainties through, you do a Taylor expansion on it, and then you truncate the Taylor expansion to a very small order, like first order, for example. And then you do a little bit of analysis on that. So I'm gonna have to remind you what Taylor series expansion is. I hope everybody knows what Taylor series expansion is. But there are different flavors of Taylor series expansions depending on what actually you are expanding. Is it a scalar function? Is it a vector function? So we're going to clarify all that. And then I will use the Taylor series expansion to develop what is known as the Laplace approximation, which is basically the most common approximation for probability density function. So basically, you're given a probability density function and you want to approximate it with a Gaussian. Okay, so any probability function, how can I approximate it with a Gaussian? The Laplace approximation is the answer. I'll show you how it works, and I'll show you that it's just a Taylor expansion. And then as soon as we have the Laplace approximation, then we will develop the perturbative, first order perturbative method to propagate uncertainties through an expensive model. Now it will turn out that the perturbative method will require the derivative of your model with respect to the uncertain parameters. And I mean, if your model is an analytical function, then that should be trivial. But if your model is a dynamical system or a partial differential equation, then getting the derivative with respect to any parameters you may have is not trivial. And to do that, we're going to have to introduce the method of adjoints. Okay, which is just a way to get derivatives from dynamical systems or from partial differential equations. And then once we have the method of adjoints, we'll propagate uncertainty through a simple dynamical system, the one we did the last time, actually. Okay, so to wrap it up, Taylor series expansion is the basis of everything. Calculus 101 or high school is where you should have learned about the Taylor series expansion. Then the Laplace approximation is basically a way to approximate any probability density with a Gaussian. We're going to develop it. And then first order perturbative methods will allow us to propagate uncertainties through models fast meaning with one simulation, okay, but there is a catch. We need derivatives of these models, and to get the derivatives of models that are dynamical systems, we will need the method of adjoints. Okay, so keywords you need to remember. Okay, Taylor series, Laplace approximation, first order perturbative method, and the method of adjoints. Okay, let's start with a Taylor series expansion reminder. In one dimension, imagine we have a function that goes from R to R, and you pick a point in R, any point you want. Let's pick x naught, and then you can expand g of x as g of x naught plus the gradient of g at x naught times x minus x naught plus 1/2. There's the second derivative of g at x naught times x minus x naught squared plus whatever. Okay? Do you remember this? See? Okay, if you don't remember that, you're gonna have trouble from this point on, because this is the simplest thing I could write. All right, but intuitively speaking, you are approximating if x is close to x naught, all right, then the first order approximates g of x as a linear function, right? So you say it's the value of at gx naught plus, I'm moving on a line. And then when you add the second term, you're approximating g of x as a quadratic function. And if you include all the terms, you can approximate anything you want. Okay? Alright, I'll just show you how it works with a simple example, sine of x. So imagine that g of x is sine of x, and I pick x naught to be 0, and I'll start expanding around 0. So the first derivative is cosine of x evaluated at 0, which is 1. The second derivative is minus sine of x evaluated at 0, which is 0. Okay? The third derivative is minus cosine of x evaluated at x equals 0, which is minus 1. So you see that it goes 1, 0, minus 1, 0, 1, 0, minus 1, etc. So this is the series expansion, the Taylor series expansion around 0 of sine of x. And you see that you alternate between minus 1 and 1, or plus 1 and minus 1. And you get rid of all the even orders. Anyway, and if you were curious, this is how computers implement sine of x, because there's no function that gives you sine of x. You can only do addition and multiplication, and you need Taylor series expansions to evaluate these complicated functions. Anyway, so this is how the Taylor series expansion looks like for the first order of Taylor series expansion looks like for the sine. So you see that, you're missing a lot, but you're just approximating in the neighborhood of 0 with a straight line. If you go to the second order, this is actually not the second order, it's the third order. Okay, so I have a typo there. You cannot do this with the third order, with the second order. So this is the third order, and it starts looking better, and then you increase to order 5, it looks better. Order 7, it looks even better, and so on and so forth. Of course, order 7 works well from minus pi to pi, but if you go further out, it's gonna stop working, okay? Because this is a polynomial approximation. It will always go to plus infinity or minus infinity away from x naught. So it's really, the Taylor series expansion is an approximation. If you truncate it, an approximation is good in the neighborhood of the anchor point. Alright, now let's go to the Laplace approximation. And I'll tell you what we want to do. So here's our problem. We have a random variable x that has a PDF, a probability density function p of x. Okay? And our goal is to find a Gaussian approximation to p of x. So we don't really like p of x, it's too complicated, or we don't have it analytically. Let's develop a Gaussian approximation to it. Okay? Now, this may seem completely useless, but it's actually a valid way to train a statistical model, is to go to the posterior if you're doing Bayesian inference, and instead of doing anything else to the posterior, you just say, let me approximate the posterior with a Gaussian. And then you are effectively doing the Laplace approximation. Okay? So here's how it works. You need to pick a center for the Gaussian, right? And the best center that you can pick for the Gaussian is the maximum of p of x. the most probable value is the best bet for the Gaussian. And of course, but instead of maximizing P of x, you maximize log of P of x, because the log of P of x is always behaving better than P of x, and they have the same maximum. Okay, so you work with that. So x naught is the maximum, the most probable value of x. And then you take log of P of x, and you start doing the Taylor expansion of log of P of x. Okay, why do you do the Taylor expansion of log of P of x and not P of x? Because P of x is a weird function. It's like this, it doesn't go to 0, it's very skewed. Log of P of x is a much nicer looking function. So if you take the Taylor expansion of P of x, you're going to have to keep a lot of terms because it's weird and you need to capture this skewness. But if you work with log of P of x, you can truncate the Taylor expansion to a very small order. So you see, I expanded log of P of x around x naught, which is the maximum of log of P of x. And if you remember a little bit of your calculus 101, you will remember that the derivative of log of P of x at x naught has to be 0. Why? Because x naught is the maximum, right? So at the maximum, the derivative must be 0, right? So this is gone. Okay, so it is a maximum, so what do you know about this term? You remember? It must be negative, right? So this term, the second derivative must be negative for x naught to be a so this is 0, and this is a negative number. Good, okay. And of course, as you can guess, we're not going to truncate here, because this is 0, so it doesn't really give us anything. We're going to truncate here. Okay, and we're going to have basically a second order Taylor series expansion for log of P of x. Okay, so this is what we get. Log of P of x is 1/2 second derivative of log of P, evaluated at x naught times x minus x naught squared plus some constant that is of third order. Okay? Alright, now what I'm going to do is I'm going to write P of x. So I'm going to exponentiate both sides. So I'm exponentiating both sides, and you see P of x is proportional to an exponential, this thing, plus some constant that it's times some constant that I'm ignoring, okay? And look at that, it's 1/2 this number, and this number is a negative number, so it's minus 1/2 times something positive, x minus x naught. So this thing here must be the inverse variance of, minus the inverse variance of a Gaussian. Okay, so you see the Gaussian right here. Here's the mean of the Gaussian, this is minus 1 over the variance of the Gaussian. Okay, so here you go. That's the Laplace approximation for a scalar function. It says that you can approximate P of x as a Gaussian distribution centered at the maximum of the probability. Okay, so you go at the maximum, and then the variance is minus the inverse of the second derivative. It's just what it is. Okay. Let's see how good this thing is. Okay, so here's how good it is. I'm approximating the blue PDF. It kind of looks like a Gaussian, but it's not really Gaussian. It's a gamma distribution with a Gaussian, which is the green one. All right, so what I'm doing is I'm finding, so if you notice the blue one is a little bit skewed. Okay, and this skewness cannot be captured by the Gaussian. So I'm finding the maximum of the blue one. I'm going there, I'm getting the second derivative, and then I'm building that Gaussian that I've shown you, with the mean being this point and the variance of the Gaussian being the second derivative. Inverse with a minus sign in front of it. This is the Laplace approximation for an even more skewed distribution. I mean, you can do it for any distribution. You can also do it for distributions that have multiple modes, but it's a second order approximation, so you should not expect miracles out of it. And you see that you can actually make it, not look that good if you go and do it for something that is really, really skewed, like this one, right? So this distribution is has an extremely long tail and it cannot be smaller than 0, yet the Laplace approximation, it's a little bit crude. But it is what it is. It's the simplest approximation, so it's good to know about it. All right? So what do we know about the Laplace approximation? It's nothing more than the Taylor expansion of the log of the PDF of whatever you want to approximate. It uses the second derivative to give you the variance. It can be a good approximation. If your distribution looks like a Gaussian, it will be a good approximation. If your distribution does not look like a Gaussian, if it's too skewed, or if it has multiple modes, it will not be perfect, but it may be a starting point, and sometimes it is the only thing you can do. All right? Yes?
So what if we just use the mean and variance of original px and just construct a Gaussian?
That will give you a different approximation. That, how are you going to find the variance of the original one?
Integrate px, like.
Yeah, okay, that's the point, right? So the question is, why can't we just use the mean and the variance, let's say, of the original distribution to approximate the Gaussian? The answer is because to find these things, you may have to integrate, and you don't want to integrate. This approximation gives you the mean and the variance by solving, it gives you the mean by solving an optimization problem, which is simpler than integrating. And it gives you the variance by just taking a derivative, which is also simpler than integrating. In one dimension, it may seem that, okay, big deal, I could just integrate. But in higher dimensions, getting one derivative, it is much, much simpler than integrating. Right? So imagine that all you have to do is go and take the derivative. That's all you need to do. So the answer is, yes, you could do that. You would get a pretty good approximation, perhaps even better than the Laplace approximation, but the Laplace approximation is dirty cheap. Okay? All right. Any other questions about the Laplace approximation? All right, so now let's go and I want to develop the Laplace approximation for random vectors, okay, for things that are x's that are x1, x2, etc. So for that, I'm going to need the Taylor series expansion of a multivariate real function. So the function that I'm considering now goes from Rd to R. It takes a vector and gives you a number. And let's pick a point in Rd, x0, and take the Taylor expansion of G around x0. It will look like that. Okay, it's not a big deal. It's basically just like the 1D one, but you have, one component, let's say, for each dimension. It's like that. Okay, so you have here all the first order derivatives times the difference of each component from x0, and 1/2 the Hessian matrix, all the pairwise mixed derivatives xi and xj of the components times this thing, okay, plus third order effects, which you can guess they look exactly like that, but they have 1/3 factorial in front of them. Now that's good, but I would rather write it as a vector equation, okay? So you have the gradient of G at x0 transposed with this vector to give you a nice scalar number, and then you have 1/2 and the Hessian matrix sandwiched between x minus x0 transpose and x minus x0. So this is the gradient of a scalar function is defined like that. Hope everybody knows what this is. The Hessian is just the matrix of second derivatives. Okay? Any questions about this? Good. All right, so the Laplace approximation for for random vectors. Now let x be a random vector with a known PDF, P of x, and we want to approximate the PDF of x with a multivariate Gaussian. Okay? We're going to use the Taylor series expansion of log of p. around x naught, where x naught is again the maximum of the PDF. Okay? So you go ahead and you solve this optimization problem to find the maximum of the PDF. We all know what argmax means. Okay? Whatever is the point that maximizes log of p of x, give me that point. Arg means the argument of the maximization. Okay? Because I was talking to somebody, I realized that people don't really know what arg means. So don't be ashamed to tell me that you don't know. All right. So the Taylor series expansion of log of p of x. Log of p of x now it's a multivariate function, so it's the Taylor series expansion of the multivariate function. Now x naught is the maximum of log of p of x, so this thing here is 0, right? So you're done with that. This disappears. It's not there. What about this term? This is a matrix. Remember, it's a matrix of second derivatives. For x naught to be a maximum, what should happen to this one? What is the essential condition? It should be negative definite. All right, so this is a negative definite matrix. And this is good because the covariance of a multivariate Gaussian should be positive definite, and with a minus, this matrix in front, with a minus sign in front of it, it will become positive definite. So if you exponentiate now both sides, getting rid of this thing, you will see that p of x is approximately proportional to this thing, and this thing looks like the Gaussian, right? X minus the mean, good, and this thing should be minus the inverse of the covariance. So here's your approximation. The Laplace approximation for a multivariate, for a random vector goes as follows. You can approximate the PDF as a Gaussian. The mean is the maximum of the PDF, and the covariance matrix is minus the inverse of the matrix of second derivatives of log of p evaluated at x naught. Okay? So you see now that you can take any distribution you like, no matter how complicated it is, and if you can find where the maximum is, and if you can find the second derivatives at that maximum, then you can construct a Gaussian approximation to that distribution. Okay, and in hard problems where we cannot really do Monte Carlo, but we can perhaps, with a little bit of work, get the second derivative, this could go a long way. Okay. In statistical mechanics, for example, where they have really complicated things, they use the Laplace approximation pretty much everywhere. Okay. Any questions? This is easy so far. Okay. Now we go to the next step. A perturbation method for propagating uncertainties. Here's the problem, the simplest problem I could come up with. Assume that x is a random vector, okay, and that you have, it's a d-dimensional random vector with a known probability p of x, and you have a model, right, a physical model that takes x and gives you a quantity of interest that is a scalar. So it's a model from Rd to R, okay, just a scalar model. And you are interested in the random variable y, capital Y equals f of x. So y, the random variable that is this quantity of interest, if x, the input to your model, is uncertain. Okay. Now, previously we characterized the statistics of y by sampling x repeatedly and evaluating f of x and looking at the y's with Monte Carlo and Latin hypercube sampling and so on. So right now we're interested in characterizing the distribution of this random variable y, the p of y, in a way that is much faster. Okay? So, and in particular, we're going to develop a way that requires only one evaluation of f of x, only one, with a derivative. Okay? So instead of thousands or tens of thousands of evaluations of f of x, you're going to be able to do it with just one. But of course, there's a catch. It doesn't always work. Okay? And I will tell you when it works and when it doesn't work. But it's really so cheap that it should be one of the first things that you do. Alright, and this approach is called the perturbation approach because you are developing perturbation approximation, because you can take it to any order you want and you can think of it as a perturbation method. But anyway, you'll see how it works. So the first thing that you do is you approximate the distribution of the density of the original random variable with a Gaussian. I mean, this is not essential, but it simplifies things considerably. Okay? So the first step is to apply the Laplace approximation to whatever is that you are uncertain about. So by applying the Laplace approximation, you will find a mu and a sigma. Okay, and then you take the Taylor series expansion of your model about the mean of x, about mu. So the Taylor series expansion of your model is going to be f of x is your model, right? You're expanding around mu, so you're going to get f mu plus the derivative of f at mu, x minus mu plus second order effects. Okay? And now, depending on where you stop, you will get more and more accurate representations of the probability density of y. Okay, so this is it. Now we can, for example, approximate the expectation of y. Here is the expectation of y. It is the integral of this expression over here over p of x. And p of x is now a Gaussian. So you have the expectation of f of x. It's the expectation of the Taylor series expansion. Remember that the expectation is a linear operator, so you get the expectation of this and the expectation of that and the expectation of everything. This is a scalar, it just gets out. And this is a scalar, it gets out of the expectation and you get the expectation of this thing, but the expectation of this thing is 0. Because the mean of x is mu and you're subtracting mu here, so you're gonna get mu minus mu 0. So to first order, the expectation of f of x is just f mu. Okay? And the second order effect, and the next term is a second order effect. It's something that has in there the variance. Okay? So this approximation works when it is legitimate to truncate this expansion at this order, right? So when your function looks a lot like a linear function. Okay. So what about the variance? For the variance, we're going to use this formula right here. So this term here, when we just approximated it, okay, it's f mu plus second order terms. And let's work out an approximation of that. Then it's very simple. You go ahead and you take your expectation and you replace f of x with your Taylor expansion of f of x. It will look like that. And then you expand the square. So you get the square of that, plus the square of that, plus the square of that, plus the square of that, and then 2 times all the pairwise terms. So this scalar will come out like that, and then this term squared will give you the derivative of f at mu squared times this here. Alright, and then you have 2 times this times that, which is going to give you this term right here. This, you can see right away it's 0. So again, like before, expectation of x minus mu. But what about this term here? This term here gives you the variance of x. That's expectation of x minus mu squared. This is the definition of the variance. So at the end of the day, you're going to get the square of mu plus the second derivative of f at mu squared times the variance of your random vector. And with that, you can put it all together. So you can take the expansion that we just derived for that, plug in the expansion for the expectation, and you will see that, you know, this term with that term will cancel out into second order actually. Actually, this is a first order. So to first order, you are gonna get this approximation. So we have shown that you can approximate the expectation of your model by taking your model and evaluating at the maximum of your random variable. But for this to be a valid approximation, your function should look a lot like a linear function, at least in the region of mu. And the variance can be approximated by the derivative of your function at mu squared times sigma squared. This is the crudest approximation you can do. There's nothing cruder than that. Okay? And of course you can start adding terms. The term here the next term you're gonna get here is gonna be a term multiplied by sigma squared. The next term you're gonna get here is a term multiplied by sigma to the 4th power. But they would require the second derivatives to write them down. Okay, that's why I didn't include them. And anyway, with this approximation of the expectation and the variance, then you can approximate the density of y with a Gaussian with this mean and with that variance. All right, because the Gaussian is the distribution of maximum entropy that has this mean and that variance. So you could say, for example, that to first order, that quantity of interest y is distributed according to this Gaussian. Look at the mean, look at the variance. Look how simple it is, right? So it's one evaluation is all you need to do this. You just need to evaluate your model at mu, and you just need to take the first derivative of your model with respect to x. And this works well when the original uncertainty that you have for x is small. Okay? So that sigma needs to be small. If you pick a sigma it's too big and your model starts being nonlinear, then this is garbage. Okay? But, if you're lucky enough to have perhaps a very hard problem that you cannot really simulate, many times, but your uncertainties are small, then this would work. If you are unlucky and you have a problem that is hard and uncertainties are large, then wait for a few more lectures. Actually, until the end of the semester. Okay, but anyway, let's see what we can do with that with a simple 1D example. So I just pick x to be a normal distribution with mean pi over 2 and this variance 0.1 squared. And I'm not really sure if I made it smaller than that at the end of the day. I don't remember, so don't take this number literally. This is my model, sine of x exponential minus 0.5x. Okay, just to demonstrate what you can do. Of course, you can take the derivative of that at any point you want. So this is now, what is this? The blue line is the model, okay, f of x. And the green line is the distribution of the input that I have assigned, right? So the green is the probability of x, and the blue line is f of x. Let me just mark it here. Blue is f of x, and green is p of x. So what you want to do is take this p of x and propagate it through the model, right? How does this perturbative method work? So first, you find the maximum or the mean if you want. You do the Laplace approximation to p of x, which of course it's already a Gaussian, so you don't have to do anything. The maximum is there, okay? And then you go ahead and you do what? You go ahead and you take the Taylor expansion of your model around that point, which you can see here that to a very good approximation, it's gonna be extremely good. Okay, because it almost looks like a straight line. So it's really a good approximation. And of course here you see that the smaller the variance of your input, the better this approximation will be. But if you start increasing the variance, you cannot take it. You should also consider the higher orders in the expansion of f of x. But anyway, if you do this approximation, this is how it would look like. I mean, it's still not perfect, but it at least captures the shape correctly. Okay, so the blue line here is the first order perturbation approximation to the probability density of y. And the green histogram is basically the histogram of Monte Carlo samples of y. So the histogram of what you would get if you just repeatedly sample the x, pass it through the model and look at your y. So you see, it's not perfect, even though it looked like the model was not very nonlinear in this region. The approximation is not perfect, but it's good enough if you are an engineer. And here's the approximation at another point. See, at this point. So at this point, it is actually better. Okay, it is better because the linear approximation is better there. And this is another point. And this is the kind of approximation you get at that point. And if you try a really weird point, like, for example, this one over there, why is this weird? It's because the derivative of f with respect to x at that point, at the mark, it's basically very close to 0. So you should really go ahead and take the second order approximation if you want to capture what's going on there. And indeed, it doesn't quite work. The approximation overestimates uncertainty. The truth is the histogram, right? And you see that you get an approximation that has a very big variance. Anyway, this is the perturbative approximation for scalars. Now I'm going to develop it for functions whose output is a vector. Okay? And you'll see where I'm getting with that. Questions?
So in the previous graphs, we have changed the distribution of x in each plot.
Yes. I just showed you what you get for different x's. Yes.
Why is it called perturbation? Or is it perturbating something?
Because this is a very good question. So whenever you have a physical model and you have a parameter that is small, and you expand the solution of whatever you have, like a dynamical system or a PDE, in powers of this small parameter, then that approximation would be called a perturbative approximation. Now here the small parameter is really sigma square. The small parameter in this approximation is this. This is the small parameter. So what we developed is basically a perturbative approximation. Perturbative approximation is an approximation in powers of something small. The small quantity here is sigma square, and we just truncated it at the first order. So if you go ahead here and you try to add more terms in this perturbative approximation, then you would get, then you would get something that is a function of sigma to the fourth to the square here, plus something sigma to the fourth. Here you would get something to the fourth, etc. And you can increase the accuracy of that approximation by taking more terms in powers of sigma. Now, why the name perturbative? Because that's the name they picked, I guess. I'm gonna have to look at the dictionary. Okay? All right. Yes?
How we can consider higher order terms? You said that the expected value of x is equal to u and all the higher order terms cancel.
No, I didn't say that they all cancel. I say that the first term cancels. So here, in this approximation, if you truncate your expansion of f here, okay, you just ignore all the other terms. But you could continue. You add one more term there, you get a higher order approximation in everything. Okay, but let's move to the more important stuff. So now I'll show you how you can do a little bit more, solve a more serious problem. So we have now a random vector I just tried before, like before, x, d-dimensional random vector with known probability density. But now we have a model that goes from d to m. So you have m quantities of interest. Okay, more than just a scalar. You have m such quantities of interest. So now your output is itself a random vector. So that y is now a vector. And you want to approximate the probability density of that vector. And what we're going to do is we're going to develop an approximation to the density of y that is a multivariate Gaussian. So as before, we start with the Laplace approximation on x. We take the Taylor expansion of f of x, but remember now that f of x is a vector function. The outputs are vectors. So you need to use here the gradient of f, like this. Okay, so this is now a matrix, actually. It's called the Jacobian times a vector. The Jacobian matrix is just a matrix of all derivatives of all components of f. Are you familiar with Jacobian matrix? You should. Calculus 2, okay? Or 1. If you just had 1, it should be in there somewhere. But anyway, it's the matrix of all derivatives. So the number of rows here is the number of outputs that your model has, and the number of columns is the number of inputs. Okay, and this is the first approximation. The Taylor series expansion of a multi-output function truncated at the first order. And of course, here now you can again take the expectation with respect to x and truncate at this term, and you see that only this term will contribute. Here you're going to get 0, and then everything else is going to be a second order effect. And you can also take the covariance of this random vector. Okay, you can take the covariance of this random vector, and what you're going to find, again to first order, is this expression right here, which is the Jacobian matrix. It's basically the covariance of your input sandwiched between the Jacobian matrix. So it is what it is. Don't worry about it. It's going to be a homework problem. You will see why it is like that. Okay. But the characteristic is that it is between the covariance. Okay, so that's your first order perturbative approximation. You can approximate the output of your model, the probability density of your model as a Gaussian, with the mean being the maximum of your input probability density, your model evaluated at the maximum of your input probability density, and the covariance matrix is going to be the covariance matrix of your input sandwiched between the Jacobian matrix evaluated at mu. And you see how simple it is now to propagate uncertainty through a multi-output model. You just have to find wherever the maximum of your input PDF is, evaluate the model there, and find the first derivative and do this matrix multiplication. Okay, and now let's go to dynamical systems. And now it will be a huge leap, right? We went from scalar functions to multi-output functions. Now I'm going to go to dynamical systems. And you see, for scalars, I approximated the probability density of your quantity of interest with a Gaussian. For vector outputs, I approximated your the probability density of your output vector as a multivariate Gaussian. Now, for a dynamical system, the quantity of interest is a function of time, and we're going to approximate it with a Gaussian process. You see how it looks like. So now, x, again, a random vector just like before. You have a dynamical system, dy dt equals g of yx. Y could be multidimensional, that's fine. This is a differential equation with initial conditions, y naught equals y naught of x. And now this dynamical system, if x is random, defines stochastic process. You can think of this stochastic process like that. It's a capital Y of t, where it's basically the solution of this initial value problem or of this dynamical system with a random x in there. Okay, so what gives rise to randomness is that x. Okay, so this is the stochastic process in time. And what we're going to do now is we're going to approximate this stochastic process with a Gaussian process. So we're going to find a suitable mean function of time and a suitable covariance function written with time as the input that approximates this the best. Stay with me, please. Here's how we go. Again, Laplace approximation on x. Okay? Then you take the solution of your dynamical system and you take the Taylor expansion. Okay, so you think now of the solution of your dynamical system, you think of it as a function of x. Okay, but it is a function of x at different times. So at each time you can go at each time and take the Taylor expansion at each time. Right? So you can use the first order perturbative approach for the response of your dynamical system at each time. And if you do the mean, how can you approximate the mean at time t? Well, you can think of this thing here as your model, okay, just parameterized by t, take the Taylor expansion of this model, truncate to first order, you're gonna get this. Okay, what is this? This is the solution of your dynamical system when x is new. And you can also do the covariance of yt and yt prime. The solution of the covariance of your response at two different times. And again, the covariance of this process, I mean, this is the definition of the covariance. And here you just put whatever you really have, which is the response. This is a random variable that describes your response at time t, a random variable that describes the response at time t prime. You go here, you take the Taylor series expansion of this around mu. You go there, you take the Taylor series expansion of this around mu, you truncate to first order, and you're gonna get this. Look at that now. This is the variance. This is also gonna be a homework. This is the variance of the input. It's not that difficult. It looks more difficult than it actually is. Especially, you know, when I do everything in 1 hour. I'm aware of that. But, you know, let's see the highlights. So, the variance here in the middle is basically the variance of your input. And then this is sandwiched between the Jacobian matrix of your response at time t times the Jacobian matrix of your response at time t prime. So all these are things that you can easily calculate, but you know, it is a little bit trickier how to get this. So look at this term. What is this term? This is the derivative of the response of the dynamical system with respect to the parameters that are random. Okay? This is what it is. It's the derivative of the response, the solution of the dynamical system with respect to the parameters that are random evaluated at mu. It is just a derivative and we just need to find it. Okay? And we find it with the method of adjoints. So here's how the method of adjoints works. First, the problem, you have a dynamical system and you want to find the derivative of the response of the dynamical system with respect to x. By the way, this is the only way I know that you can, I mean, this concerns at least 2 or 3 people in this room, in addition to my students who should just know about this stuff. This is the only way I know that you can propagate uncertainties through the Newton transport equations. The only viable approach that I have found is an approach based on first order perturbations using the adjoint method to get the derivatives. Everyone else who does propagation of uncertainties through either an ODE or a PDE, this is also a viable approach, but you need to meditate a little bit on it. All right, so I think I should just move directly to the solution, and I will educate you on that with a homework problem, I promise. Okay. But I'll just show you very quickly. So what is the idea? The idea is to start with your dynamical system and then derive a set of equations, a set of differential equations that the derivative must satisfy. Okay, so you have your original differential equation, and then you add a bunch of differential equations that the derivative with respect to the parameters must satisfy. And this set of equations is called the adjoint differential equation, or the adjoint dynamical system. And you just need to solve them simultaneously. Okay? This is how you do it. And you can also you can do that for dynamical systems. You can do this for partial differential equations. And it's very, very simple. All you have to do is ask, you take the derivative right there. Here's the derivative with respect to one of the parameters. And you say, let me just use a little bit of math to take the derivative of the derivative with respect to time. And when you use your math and you are, well versed in the chain rule, that's pretty much all you need, you will get a very nice dynamical equation, a very nice differential equation for the Jacobian matrix. So this is the differential equation that the Jacobian matrix must satisfy. And it's really very simple. You can actually calculate all of these things analytically in most systems. And in addition to this differential equation that Jacobian must satisfy, you can also find initial conditions for the Jacobian. And you can show that the initial conditions of the Jacobian are the Jacobian of the initial conditions of the original system. And then this constitutes the adjoint dynamical system. Now this is the problem that we did the other time. So you see, it's a very simple differential equation, exponential decay. We have two parameters, the decay rate and the initial condition. And now I used whatever was in the previous two slides to derive two differential equations that give me the derivatives of y with respect to x1 and x2. And these differential equations constitute the adjoint system, and this is how they look like. So they're not anything spectacular, right? So the unknown quantity here is these things. Right? The derivative of y with respect to x1 and the derivative of y with respect to x2. So you see it's a simple linear dynamical system that you have to solve in addition to the original one. So you see the original one acts like an external forcing to this dynamical system. And the initial conditions are like this. But anyway, so here's so imagine here your problem, right? And here the adjoint system for your problem. So Newton transform equations, I don't know how much, 6-dimensional or even higher dimensional than that. Another bunch of equations right there that need to be solved simultaneously. And here's how good this approximation is. So here you see the mean estimated by Lightning Hypercube, 10,000 samples of Lightning Hypercubes. And I compare that to the mean you get with the perturbative approach, which is just one simulation. Okay, this is just one simulation. And the green line is the variance with 10,000 Latin hypercube samples. And the dashed line is the variance with one simulation. But solving also the adjoint system to get the derivatives. Okay? So you see that it's not perfect, but at least you get the shape right. and it is ridiculously cheap if you ignore the cost of developing the adjoint equations. But this is pretty much it. Is anybody here using Phoenix? Have you heard of Phoenix? Anybody using finite elements, finite volumes? Okay, you. Good. So, do you know Phoenix, which is a finite element package for solving for Python? Phoenix. So, Phoenix is a finite element package that allows you to define the weak form of your PDE, and it creates a finite element solver for you, and it can give you for free the adjoint solution. For free. You don't have to do anything. You just tell it, give me the adjoint. Okay? You could implement Newton transfer equation in Phoenix, and you would get the adjoint automatically. Okay. But of course, this is just the variance and the mean of the Gaussian process. You can actually, get predictive, 95% predictive intervals for this. And because we have approximated the response is a stochastic process, which we have approximated as a Gaussian process, we can actually take samples of it. It's a Gaussian process. We have the covariance matrix. We have estimated it using a perturbative approach. So we can sample from it. The samples look like that. And they look hopefully like, they look just like the original samples if you don't pay too much attention to it. Alright, anyway, I realized this was a lot. But it is what it is. I'm sorry. Okay, it is that hard. Next time we'll talk about, so what have we seen? How to propagate uncertainties by sampling. Fine. 10,000 samples. Can you afford it? You can do it. Okay, no problem. What if you cannot afford it? Then you need to do math. This is the only way you can solve a problem. If it is very hard, it's to sit down and do some math. You show a method that does one sample and give you an estimate of the uncertainty. Okay. Now, next time we're going to talk about methodologies that you can use for propagating uncertainties that extend this. Okay, so that you should use when you cannot really truncate these functions at the Taylor series expansion at the first order, but you have to retain more terms. We'll start looking at methodologies that look like that. Now, may look like I'm going too fast. I can see it in your faces. You get over it, okay? You get over it. So let's go with, let's start with the handout. Hopefully you will be able to understand a few things from the handout.